Today we're gonna take a look at Secureum RACE number 9, which was, I think, the first race that I had the personal honor to design. It is a little bit similar to race number 12, which also had a lot of delegate-call stuff, but this very explicitly is centered all around a proxy, an ownable proxy basically. And this proxy is a little bit special because here you don't just have one implementation that the proxy can point to, but rather than that you can have multiple implementations, and the proxy decides based on the function signature that is being called which of these implementation the call should be forwarded to basically. So this means that every time you want to execute some function of this protocol, you would just send your normal function request to this proxy, and then this proxy looks up the message.signatures, message.sig, which is the function signature. So this contains the 4 bytes of the hash of the function's signature. So a kind of a unique identifier. It's not super unique, but it is sort of a unique identifier for a function, for an external or public function. And based on this function signature, it then determines the implementation from this mapping. The implementation is then loaded into this local variable, and then a normal delegate call proxy forwarding is done. This assembly code here, you don't really have to understand it. It has been copied without changes from OpenZeppelin's proxy contract, so there's no issue with this assembly, and you can just take it for what it is for now. And furthermore, it is an ownable, it is an owned proxy, because there is a set implementation for selector function, which can be called by the owner to set a implementation address for the specified bytes for signature. So you can basically upgrade, for example, if you updated one of the functions in the protocol, you can deploy only that new function, or code containing only that new function, and then point the function signature to this new implementation that you've uploaded. So this is a really nice kind of pattern for a contract that was too large to be deployed as a single contract, and instead it had to be split into multiple parts and distributed among multiple contracts. But it is still kind of complicated to handle, because you have to make sure that none of these different implementations have any clashes in between. That means that all of these implementations, they all access the same storage. And that means that you have to be really, really sure that you don't accidentally access the incorrect slots, which then clash with other slots from other contracts, which makes things a little bit difficult, but it is possible. So let's put it that way. It's not impossible to get this right. It's certainly possible to do this the right way, and it is kind of a cool pattern. And this entire proxy here is basically deployed for the implementation contract, which we call the master copy, which also extends the ownable. So that means that for both the proxy and the master copy, if we get the current owner, for both the owner will be the same. So if we get the current owner directly on the proxy, the owner will be the proxy of the owner will be the owner of the proxy. But if we call a function within the master copy through the proxy and it checks who the owner is, then the same owner slot as in the proxy is accessed basically. I hope that makes sense. So this master copy contract is a very simple counter contract. It has a public counter storage variable which can be increased or decreased. And yeah, that's pretty much it. So let's take a look at the first question, which says that the function signature is the first 4 bytes of the Ketchuk hash, which includes the function name, includes a comma-separated list of parameter types, includes a comma-separated list of return value types, or D is generated only for public and external functions. So there's actually this neat website called openchain.xyz, which has a signature database. And here we can just look for a function, for example, transfer from. And we have here, for example, the transfer from credit underscore EV function, which takes an address, and a UN256. So this is probably from some verified open source contract that has been deployed live. And the function signature belonging to this function is 009679 and B5. So this is these are the first 4 bytes of the Ketchak hash of this function. And it is created from the function name and the list of parameter types. So with that, we can say that it includes function name, the comma-separated list of parameter types, but it does not contain a comma-separated list of return value types. So that means even though some transfer functions return a boolean and others don't return anything, both of these functions will still have the same signature because both transfer from functions have the same types that they receive as parameters, basically. Then D is generated only for public and external functions. So basically what happens when you call a function on a contract is that basically a contract really only has one entry point, and that's the first byte. So you have a program, this is the contract, and when you want to call a function in this contract, the EVM has no idea about functions. For the EVM, there are no functions, no such thing as functions, there are only calls. This call then invokes the contract code at this other address, and then this contract code starts from the first byte of the bytecode. So it doesn't just start in the middle of the bytecode depending on the function. No, it always starts at the first byte of the bytecode. And the first few bytes of the bytecode, well, the first couple bytes, they basically just set up the memory layout of Solidity. And then immediately after that, we get to the function selector, I guess. And the function selector then jumps to the part where this function, where the function's code that should be executed for the call is located based on the function signature that was passed as the first 4 bytes of the call data. So basically the bytecode then loads the first 4 bytes of the call data, and it then goes through a list. Goes through a list of all the external and public functions that it has. So as I just said, these function signatures are only generated for public and external functions. And basically this is a bunch of if clauses. So if the first 4 bytes in the call data are equal to the function signature of this function, then go to this part of the code. Else, if it is equal to the function signature to this other function, then go to this other part of the code. And like that, the right part of the code is basically jumped to, and then this external function is executed. So it is indeed only generated for public and external functions. And that's the whole process of a function signature, basically. And that is question 1. Next, we have question 2. Which says that the proxy contract is most similar to a UUPS proxy, a beacon proxy, a transparent proxy, or a metamorphic proxy. So UUPS stands for Universal Upgradable Proxy Standard. And a UUPS proxy is the kind of proxy where the logic of the proxy itself is not stored within the proxy contract. So if we look at the proxy contract that we have here, we have a fallback function, but we also have a public implementations function here for this mapping, and we also have a set implementation for selector function. And these both are part of the proxy, and the danger with that is that one of these implementations might also have a function called implementations or a function called set implementations for selector. And the problem of that is that when this clashes, that means that the code, that this function behind the proxy becomes unreachable, because every time you try to call the set implementation for selector function of an implementation, it will always be caught first by the proxy, because it never reaches the fallback function that would trigger the implementation of that function. Because the fallback function is only executed when the function selector, going through this if, else, the fallback is basically the last else. If nothing else matched with the function selector, or none of the function signatures matched, then else do the fallback. But in this case, set implementation for selector would be found, and therefore the fallback would never be executed. So UUPS proxies solve this problem of potential clashes by basically moving the logic of the proxy itself. So the logic, for example, meaning that the function to upgrade from one implementation to another implementation, or here the logic to set an implementation for a selector, would be part of one of the implementations, with the advantage being that for one, you can more easily avoid clashes between functions, and second, you would be able to upgrade the proxy's own logic. So if you want to change how the proxy works, then you could simply upgrade the implementation, which also upgrades the proxy itself. But it also has a big drawback, because UUPS proxies can get bricked very easily, because if you upgrade your proxy to an implementation of which the upgrade functions of the proxy are broken, then you cannot upgrade anymore. So if you upgrade it to a broken implementation, suddenly the proxy itself is also broken. So it has advantages and disadvantages. But in this case, it is definitely not similar to UUPS proxy, because we have the proxy logic within the proxy itself. Then a beacon proxy. A beacon proxy has a beacon. It follows the beacon pattern. And what that means is simply that the implementations wouldn't be stored within the proxy contract itself, but rather than that, it would make a call to a beacon contract, and ask that beacon contract, hey, what's the implementation? Give me the implementation address that I should delegate call to. And this is a normal call, which returns the address that should be delegate called to, and then it does the second call, which is the delegate call to the actual implementation according to the beacon proxy. So a beacon proxy is sometimes necessary to be more flexible, because, well, for various reasons. For example, because the proxy is used by various people, and depending on who's calling, we want to have different implementations or something like that. But there are reasons for using beacon proxies, even though they're a little bit more expensive. But we do not have a beacon proxy here, because we are not making a call to another contract to ask for the implementation. All of the implementations are in this proxy, are stored in the storage of this proxy. So this is not a beacon proxy. Then option C says that this is a transparent proxy. And that is correct, because a transparent proxy is exactly what we have here. A transparent proxy is a proxy where the logic of the proxy itself is stored, or is part of the proxy, and not part of the implementation. So it is certainly most similar to a transparent proxy. And then we have D, a metamorphic proxy, and that's not really a thing, that doesn't really exist. You could, well, what is metamorphic? Metamorphic is basically when you created a contract with like create2 in such a manner that you could recreate a contract with different bytecode at the same address. That means you could delete the implementation and then recreate a different implementation, but push it to the same address. And that is a different way on how you can upgrade a contract without using proxies, which makes calling them cheaper, but makes the deployment a little bit more expensive. But also the metamorphic pattern will not exist for much longer, because soon the self-destruct opcode will no longer work. Soon you will no longer be able to destruct contracts, and no longer be able to delete their bytecode, and therefore this metamorphic pattern will be lost, which is a little bit sad, but it is a necessary measure to introduce to move from, I think, Merkle trees to Verkle trees, which is much more efficient and better for Ethereum scalability, and that is the reason why this self-destruct has to be gotten rid of. Although you could do a few fun things with it, I guess. So that's question 2. Our proxy here is most similar to the transparent proxy. Next we have question 3, which says that gas will be saved with the following changes. A. Skipping the initialization of the counter variable. So do we have a counter variable? Yes, we have a counter, a public int256 counter variable in master copy, and it is initialized with 0, which means that during the construction of this contract, the storage slot where the counter variable is stored will be set to 0, but that is unnecessary because, as we know, all of the storage variables are 0 by default, so there's no reason to set it to 0, and setting it to 0 would just be a waste of gas, basically. So we could indeed skip the initialization of the counter variable. It would still have the same value, and we would be able to save some gas doing that. Then B, making the increase function external to avoid copying from call data to memory. The increase function is also in master copy and is currently public, and we are supposed to change it to external. So would that change prevent copying from call data to memory? Well, in the first place, there's nothing being copied from call data to memory here because it does not have any parameters at all. So that option just doesn't really make sense. And even if it had parameters, just changing it between public and external doesn't change whether it is copied or not copied. This has more to do with what is being specified here. If the parameters by reference are to be stored in memory, then they have to be copied from call data, because when the parameters arrive, they always arrive from the call data. So if the parameters here would specify memory as the data location, then they have to be copied. But if we would change this function to external and it had call data, it had parameters with call data, then we would be able to skip the copying process because they don't have to be moved into memory. But we could even use external reference variables with the call data location. In public functions, the only problem then is that this public function wouldn't be internally callable that easily, because it would expect one of the parameters to be within the call data, and it's not like an internal function would be able to, or an internal call, so a call from one function to the other within the same contract without making an actual external call. You cannot exactly, pass something via call data, because call data is write only. So call data is read only. You cannot write to call data. So it wouldn't be possible. It wouldn't be possible to that easily internally call a public function that makes use of call data parameters. But that is taking it too far. It doesn't really have anything to do with what we have here. The important part is that this increase function doesn't even have any parameters in the first place, and that makes it not possible to save any gas here by changing it to external. Then we have C, packing multiple implementation addresses into the same storage slot. So you might have heard that we can pack multiple multiple storage variables into using the same storage slot. So storage slots are always 32 bytes big, and we have some types that just don't need that much room. For example, 2 uint8, so two unsigned integers that only take 8 bits. Together they would only take 16 bits, and that's more than enough to put into a 256 bit slot. So those two could be packed into the same slot together, and this makes a lot of sense, especially if both of these variables are very often loaded together anyway. So in that case, you don't have to load two separate storage slots. You can always just load one slot, then split these slots apart, and then you have both of these values basically. And packing multiple implementation addresses, so basically in this mapping here, where we store the implementations per message signature, per function signature, is not possible because an address is 20 bytes long and a storage slot is 32 bytes long. So packing two addresses into the same slot isn't possible. We could like pack half of an address in one slot and the other half of an address into the other slot, but that doesn't really make sense because we never load more than one implementation per call, and then you would have to load two slots to construct an implementation out of two halves. It just doesn't make sense. So C, packing multiple implementation addresses into the same slot also can't really be used to save gas. Then we have D, moving the calculation of the counter function's signature hash to a constant. So we have here in the constructor, we are calculating the function signature of the counter function. So the counter function is basically the function that is automatically added by Solidity to access this public storage variable. And to calculate such a function signature manually in Solidity, we just convert the string to bytes, then we hash it. We hash this byte string, and then we only take the first 4 bytes of this byte string, and that is then basically the 4-byte function signature of the counter function. So could we save gas by moving this into a constant? Well, it would only save gas if that constant would then mean that the compiler is doing this calculation off-chain and then stores the already calculated 4-byte value within the constant, which is then used in the constructor, but that's not what happens. If we would move this entire part here, this entire calculation here into a constant, what actually happens is that when this constant would be accessed here, it would just evaluate the same expression that is being evaluated as if it was directly in here. So there is no difference because either way this is going to be executed either directly here or when you're trying to load the value of that constant. So it just doesn't make any sense, and it wouldn't save any gas. It might improve readability, so it might be worth to do it for purposes of readability, to move it out into a constant. Why not? But in terms of saving gas, it doesn't really do anything at all. So in this question, only skipping the initialization of the counter variable is saving gas. Things are going to get really interesting now with question 4, which says that calling the increase function on the proxy contract will A, revert, since the proxy contract has no increase function, which is technically correct. It has no increase function, so will it cause the proxy to revert? B, it will revert for any other caller than the one that deployed the proxy. So the person that deployed the proxy needs to call the increase function, otherwise it will revert. C, increases the integer value in the proxy's storage slot located at index 1. So this starting from index 0, which storage slots do, from index 0 to 1 to 3 and so on. And that means that if the increase function is executed, whatever is stored at index 1, so in the second storage slot, will be increased by 1. Is that correct? Or D, it makes a delegate call to the 0 address. So let's first take a look at what happens when the proxy is deployed. So what happens is that the constructor is executed, and the constructor first creates a new master copy. So it creates this contract, it deploys this contract, and next it will set an implementation for the counter function, which is the which is the function belonging to this public variable, and it sets the implementation address to the master copy. Then we have again an implementation, another function selector set as one of the implementations, which is the increase functions selector. So instead of this time manually calculating the function selector, instead it takes the master copy contract, makes a dot, then selects the function, the increase function, and gets the selector of that function, and also assigns to this function selector the master copy. And this increase function is the one that this question is about. So we can see that if the fallback then is called, because there is no increase function on the proxy, but that doesn't make the proxy revert. Instead, the fallback function is executed. The fallback function being executed means that it will try to load the implementation belonging to the function signature. The function signature that we are sending in the call data is belongs to the increase function, so it will return the master copy address. So the implementation address stored here will become the master copy address, and that means we are then delegate calling to this implementation, which also means that we're not delegate calling to the 0 address as one of the options suggested, because we have successfully loaded an implementation assigned to the increase function signature. So when that is executed, then that means that we are the proxy is delegate calling to the master copy, which then finds that it does have a function with a function signature for increase, and then this function is executed. But this function has an only owner modifier. So who is the owner in this case? Well, from the master copy, when calling the master copy contract itself that was created here during the constructor, who would be the owner of the master copy? In that case, the owner of the master copy would be the proxy itself. But if we call the master copy through the proxy, then the owner of the master copy is the deployer of the proxy, because that's what Ownable by default does. By default, Ownable assigns ownership to whoever deploys the current contract. And because master copy and proxy both share the same storage slots of the proxy when master copy is called through the proxy, because it is being delegate called, that means that then master copy is basically owned by whoever deployed the proxy. So we can say that it will not revert just because the proxy doesn't have an increase function, because the fallback will be executed, which delegate calls to the master contract. It will revert for any other caller than the one that deployed the proxy. That is correct because of the only owner check of the increase function. And then, so let's say that the caller is the owner. The increase function was it? Or let's say the increase function is executed and the caller is the owner. So this only owner modifier passes, which means that this counter is executed, ++ counter. This increases and updates the counter value to the increased value and then returns that increased value back to the owner. So that means that there is definitely a storage slot here. The storage slot at which counter is stored is being increased. But this seems to be the first storage slot. So why would it be at index 1 instead of index 0? And the reason for that is because of the owner storage slot. Because basically the lowest contract that we are inheriting from, those storage slots are reserved first for the lowest one. So in this case, the lowest contract that we are inheriting from is the ownable contract, which means the ownables storage variables will come first in the order in which they get their storage slots assigned. Ownable has exactly one storage slot, which is the storage slot that stores the owner. So at index 0 of the storage slots, we will have stored the current owner, and at index 1 of all the storage slots, we will have the counter variable. So I hope that's clear, and therefore, indeed, at the slot at index 1, this counter will be increased. So see, this increases the integer value in the proxy's storage slot located at index 1, and it does not delegate call to the 0 address. Next, we have question number 5, which is very similar to question number 4, but this time it is not about the increase, but the decrease function, and what happens if you try to call the decrease function on the proxy contract. Will it revert because it was not correctly registered in the proxy? B, will it succeed in return the value of counter after it was decreased? C, will it succeed in return the value of counter before it was decreased? Or D, will it succeed in return nothing? So if we look at the constructor of the proxy, we can see that there was an accident here because we have increase function registered as implementation 2 times. This second time should probably have been the decrease function, but instead it is the increase function. So what happens now if you try to call the decrease function which has not been assigned any implementation? You might expect it to revert because that is an invalid function basically. But what actually happens is that the implementations mapping for the decrease function signature will just return the 0 address, the default 0 value for an empty mapping value basically, which is the 0 address. So address implementation will be 0, and then it will go ahead and just do a delegate call to the 0 address, and that will work because to the EVM it doesn't really matter what it is calling. If it's calling a contract that has code or an EOA, it will just do that, and it will just see whatever is being called. And if the delegate call target that is being called just doesn't have any code, it will just kind of implicitly assume that it only has 1 bytecode. Even though it has no bytecode, it will assume that it has 1 opcode that is executed, which is the stop opcode, which is a successful stop executing of the contract. So the delegate call made to the 0 address will succeed without issue, and it will just not return anything, but it will also not revert. So for question 5, it will not revert because it was not correctly registered. Instead, it will just succeed and return nothing. So these 2 other options here, they were kind of bait because, as you might have noticed, we are doing plus plus and then counter, and here minus minus and then counter instead of the more common way to do it, which is counter plus plus, counter minus minus. And the effect, whether you put it in front or after, is basically that the value that you return here is different depending on where the pluses are. So in this case, how it is currently, it means that it first increases the counter and it then returns the counter after increasing it by 1. And if it were the other way around, if the plus plus were at the end, then it would return the counter value before it was increased, basically, and not return the value that was done after the increase. So that's what's going on here, and I didn't. It looks like I'm going to ask about this, but I wasn't actually going to ask about this, and instead it was just kind of a bait and switch, because it made these other two bogus options sound more enticing and realistic to choose, basically, but they don't make sense. So for question 5, it will just succeed and return nothing because delegate calling to the 0 address just works, and that's question 5. Next, question 6 says that due to a storage clash between the proxy and the master copy contracts, A, the proxy's implementation would be overwritten by 0 during initialization of the master copy. B, the proxy's implementations would be overwritten when the counter variable changes. C, the proxy's implementations The proxy's implementation's variables storage slot being overwritten causes a denial of service, or D, none of the above. And if we look at the code, we can see that both proxy and master copy define their own storage variable here, and they both come after ownable. So if the first storage slot at index 0 is the owner, and the storage slot at index 1 is the counter for master copy, well, then what happens with this mapping, which is also at the same place where the counter is for the master copy? Isn't there a storage clash problem here? And the answer is actually no. There's actually no problem here, and that's kind of weird. And I think to explain this, we will actually do a little bit of drawing. So both the proxy and the master copy contracts are inheriting from the ownable contract. So they are both inheriting also its storage variables. And it has exactly one storage variable, which is the owner. Proxy also has one storage variable, which is the implementations mapping. And the master copy contract also has one variable, which is the counter storage variable. So if you compile the proxy, the storage slot at index 0 would become the owner's storage slot, and at index 1 would be the implementations mapping storage slot. And for the master copy contract, when you compile the master copy, you would get an assignment where the first one is again the owner, but the first, where the 0 slot basically is again the owner, but the slot at index 1 is the counter. So isn't that a storage clash? Well, for that we actually have to understand how storage works in a little bit more detail. So let's talk about storage real quick. It is a key to value store where both the key and the value are 32 bytes large. So you can say I want to store at these, so the 32 bytes can be anything. It doesn't have to be 0. You don't have to start at 0 or anything. You can just pick any random 32 bytes and say at this key I want to store that value. And later you can come back and say, give me the value that is currently stored at this key. And Solidity manages the storage slots in this way that it begins from the 0 slot. So all of these 32 bytes are 0 basically, and it then stores the owner at the key 0. So what happens with these two? So the master copy contract would also store its counter value at the index 1, but the implementations isn't simply a single value, it is a mapping, and mappings aren't stored at a single storage slot because that wouldn't be possible, right? As we already said, we can't pack multiple addresses into the same storage slot. So how does an implementation, or how does a map of addresses even work? It works in this way that, like, the implementations itself is also like a key value store. So we have implementations, and we access or store a value by specifying the function signature here and assigning it an address. Oh boy, I need to practice writing more. Anyway, so what happens to this signature is then that the signature is hashed together with the storage slot that it has been assigned to the implementations mapping. So in this case, it is the storage slot 1. So 1, and then it also adds in the signature. and the result of this hash is the actual storage key. And since hashes are kind of random, so the result of this hash will be some very big number or some very random 32 bytes. So at these very random looking 32 bytes, this implementation of this signature, this address will end up being stored. So at the end, there is actually no clash between the counter and implementations. This is completely fine, even though it should be avoided because, well, this is kind of fishy, I guess. You probably shouldn't do it this way. So why does... So in a way, implementations, the mapping is reserving the storage slot 1 for itself, because if the proxy had another storage variable such as counter later, then counter would end up at the second index instead of at the first, even though implementations isn't even using this one. And the reason for that is simply that if we have multiple mappings, we want to make sure that the mappings themselves don't clash, and we ensure that by including the storage slot of the mapping into the hash that then determines where it is. So imagine we have two mappings and we want to store at the same key for both mappings, we want to store a value. So to make sure that these two, that we don't get the same hash for both mappings, we need to add something in, and that something that makes a difference between both mappings is the storage slot that has been reserved for the mapping, basically. So I hope that explains what is going on here and why this storage clash is not a problem. So that means none of the above, because even though the implementations has this storage slot at 1 reserved, which is also the storage slot for the counter, they don't ever clash. There is no problem. No implementations, no addresses are overwritten, so A can't be true. And so it is no implementations, no addresses are overwritten when the counter is initialized, and nothing is overwritten when the counter variable changes. So none of the addresses that are stored in the implementations mapping would be overwritten because of that. And it also doesn't cause a denial of service because of this kind of clash, but not really clash. So therefore, none of the above are true. Then question 7 says that the proxy contract won't be able to receive any ether when the call data size is 0 due to a missing receive function. Well, that is in this case not true, because this fallback function actually is payable. So even if the data size is 0, this fallback function will still be called and will still be fine with receiving value because of that. So this is not true. B, the proxy contract will be the owner of the master copy contract. Yes, we already talked about this. So basically in the constructor, the proxy is constructing the master copy, and in ownable, which master copy is inheriting from, the default is that the owner is by default whoever deploys the contract. So indeed, the master copy will be owned by the proxy. So that is correct. C, the proxy contract has a storage clash in slot 0, which will cause issues with the current master copy. We already looked at the memory layout, and we have seen that for both the proxy and the master copy, the storage slot 0 will be assigned to the owner from ownable. So there is no storage clash here, because that is intended to be this way. Both are used for the same purpose. So there's no problem with that, and none of the above can't be true, and that is question 7. Finally, we're looking at question 8, which is about the fallback functions assembly block. So let's just walk through this assembly block and what it does. So the first thing it does is a call data copy with parameters 0, 0, and call data size. So call data size obviously returns the size of the call data that was passed to the fallback. So when we are calling the proxy, we're calling the proxy with a function signature and with some parameters, and all of these things are all contained within call data, and then call data size is the length of all of this data. So if it is only a function call without any parameters, that means the call data only has a function signature. That means then that the call data size is 4 bytes. But what does call data copy do? Obviously it copies call data, but what do these zeros here mean? And we can look that up by going to evm.codes, and we can look here for call data copy, and the description says that copy input data in current environment to memory. So we are copying from call data to memory. It says here destination offset. So destination offset is to where in memory we are copying it, and then offset from starting from where are we copying from call data, and then size, how much are we copying from call data. And that makes perfect sense, right? Because we want to copy all of the call data, because we want to forward all of the call data with a delegate call to the implementation. That means that we also have to copy all of the call data into memory first. So we are copying the call data to memory starting at memory offset 0. Then we are starting to copy, so it is going to be stored, to be copied over to memory starting at 0, and we are copying it from call data, from the 0 offset in the call data until we have reached the full call data size. So visualizing this, I guess you can do it like a bit like this. We say this is call data, and it starts at 0. It just is like kind of like an infinite kind of band, and if it only has a function signature, so sig, then it goes until here, and starting from byte at offset 4, there would be nothing, or if there are parameters, then the first parameter would be in a 32-byte slot basically. And the second parameter would also be its own 32-byte slot starting after the function signature. And when we do call data copy, then we are moving the call data to memory. So we have the memory, which is also very similar to call data, like an infinite kind of tape, which also starts at 0. And when we are doing call data copy with the maximum size, so the size, if this is all we have, then this is the size. And when we are starting to copy from 0 to size, that means we are just copying 1-to-1 sig, the first parameter, and the second parameter over into memory. So now memory is 1-to-1 like call data is, with the difference that obviously we can't write to call data, and we can't do that much with call data as we can do with memory. So the next thing that we're doing here is doing a delegate call. So we are passing to this delegate call, we are passing guess. When we execute the guess opcode, what we get in return is how much guess do we have left right now. And the first parameter that we have in delegate call is how much guess are we passing onto the contract that we are calling, basically. The second parameter is the address that we are calling, which is the implementation. That makes sense. And then we again have 0, then we have call data size, and then we have 0, 0. And we can see here that the first one is args offset, the second one is args size, so 0. So the parameters that we are passing, the arguments that we are passing in as part of the delegate call, they start at offset 0 in memory. How long are they? Even though they are now in memory, they still have the same size as the delegate call, as the call data, because we copied everything from call data into memory. So now everything that is in memory that we care about is until that point. And then we have return offset. So the return value that we get back from the delegate call, where should that be stored to in memory? And the return size, how much of this return data should we store in memory? So what we can see here is that it basically says that from 0 to call data size. So from 0 to call data size, which is the same size as the call data was. Oops. Here. So that's the same size. So we're making use of the entire memory that we copied from call data, and we are passing it over to the delegate call. And we're also telling the delegate call that the return values from this delegate call shouldn't be copied at all, apparently, because we are saying that you should copy it into memory starting at offset 0, so it would overwrite the call data that we've copied. But then we are telling it how much should it copy? It should copy 0. So at the end, nothing is copied. But that is then made different in return data copy. Return data copy copies output data from the previous call to memory. And now we have access to return data size. Now the problem that we had when we did the delegate call was that we didn't know how big is the response of this delegate call going to be. We didn't know because we haven't done the call yet. It could be anything. So we couldn't specify a return length here. So instead we first do the call and we copy nothing. And then when we have done the call, we can do return data size, which will give us the size of the returned data from the last call. And then we can use this to, just like call data copy, we're now copying from the return data. So return data is basically like call data. It's a read-only thing, which always contains the returned data of the last call. So very similarly, we now, after the delegate call, we have return data, which also goes from 0 to wherever, like an infinite tape. And we now got some sort of return data. We don't know what it is, but we know after doing the call, we know that it is this long, that it has this size. And then we are doing this return data copy to basically copy from starting from 0, so starting from there until size, so until here, and we're just copying from there to there, and we're just overwriting the call data that we've previously copied, and now the return data is contained also within memory. We no longer care about the call data that we copied into memory because we've already used it, we've already done everything that we wanted to do with the data, so we don't have to bother maintaining the data, so we can just overwrite the call data that we had copied over into memory. And then depending on whether the call is successful, so basically this delegate call, it will push one result to the stack, either a 1 or a 0. It will be a 0 if the delegate call reverted, and then we will revert with the returned data. Or if it didn't revert, if the delegate call didn't revert, we will return like a successful, everything went fine return, and we will also return the returned data, which is the equivalent of like when you revert, you are reverting with an error message, right? So this error message would then be part of this return data that we just copied from the return data from the call, basically. But and we are reverting by specifying that this error message that we have already copied into memory, it is at memory starting at offset 0, and it is this long because we've copied all of it into memory, all of the return data, and the same is true for default. So when the delegate call was successful, then we just want to return all of the return value that we have received back from delegate call, starting at memory offset 0, and all of it. So now we have walked through the assembly block, and now we can go through the options. So option A says, can the assembly block of the fallback function be marked as memory safe for guess optimizations? So memory safe means that this assembly block respects Solidity's memory layout, if you Google Solidity memory layout, you will find the following page, which tells you that Solidity reserves the first 4 32-byte slots with these specific ranges, and it expects you to respect these. So the first 2 32 bytes are used as scratch space for hashing methods. The next one is for managing the memory, how much has been allocated already, where can I find the next free memory, and the last one is the 0 slot, which should always be 0 because sometimes Solidity just needs a whole bunch of zeros in memory. And do we respect this? I would say we don't, because as we said, we are just writing starting from 0. We are just overwriting first the call data into it and then later the return data into it. And as we can see in this layout in memory, starting from 0 and then going the first 4 byte slots, these are actually reserved. So we are in fact writing into reserved memory here while doing all of these things. And you can certainly not say that we are respecting the Solidity memory layout here. And we can therefore also not mark it as memory safe because of that. But why is it doing that? Why is it not respecting the Solidity memory layout? Well, it does it for simplicity and maybe even for guess optimization purposes, because it doesn't need to care at this point, because it is the last thing that is going to be executed at the end of the fallback function. It would be different, it would be a different story if after the assembly block there would be more Solidity. If there would be more Solidity being executed. But as it stands now, what happens is that this assembly block always either reverts or returns, which destroys the current environment, the current EVM context, and after that nothing else can happen. So even if you would write code after the assembly block, it is unreachable unless we change the assembly block. And since the memory after this assembly block is thrown away anyway, and no more Solidity specific code is executed after this, we can just ignore it. So why is this talking about guess optimizations? The reason for that is that the optimizer in the newer Solidity versions can actually handle memory blocks. It can actually rearrange the assembly coming from the Solidity code and the assembly from your own assembly blocks, and it can mix them together and find a way how they can work very efficiently and make gas savings. But it will only do that if this block, your assembly block, is marked as memory safe, because it knows that if you don't respect the memory layout, it is too dangerous to start mixing your assembly code with assembly code of the rest of Solidity, because the rest of the Solidity code would expect the memory layout to be respected. So can we mark it as memory safe? No, because first of all, it doesn't respect the memory layout. And second of all, this version of Solidity isn't even compatible with this yet. So there is no memory safe flag in this Solidity version yet. I think that comes with 0.8.13. 0.8.7 doesn't even have this flag yet, so we can't even mark this assembly block as memory safe, even if we adjust it to be memory safe. So that wouldn't do anything in this case. Alright, so that was A. Then we have B. The result of the delegate call overrides the call parameters in memory. We've already seen that. As we said, the return data writes into memory, overwriting the call data that we've copied, which are the call parameters. So yes, that is indeed happening. Then C, it interferes with the slot hash calculation for the implementation's mapping by overwriting the scratch space. So the scratch space are the first 2 32-byte slots of the memory, which is scratch space used for hashing methods. And we've already talked about how accessing a mapping requires hashing this function signature, so this key of this mapping. It will be hashed together with the storage slot index that this implementation's storage variable is reserving. So hashing needs to happen here. The question is, does this influence this hashing negatively? The answer is no, because this is already done at this point. So when the assembly block is being executed, all of the hashing to get the implementation from the mapping has already happened. There is no interference there. So C is not true, none of the above cannot be true, and therefore for question 8 we have B. And that completes race number 9. So while editing, I was thinking that it might still not be quite clear what is happening here in regards to what is the interplay between the delegate calls and the storage slots that are being used. So I will, just in case you haven't understood everything yet, I will give it one more try to explain it by drawing a little bit and hope that that clarifies things. So when we are deploying the proxy contract, this proxy contract at the storage slot 0 has the owner, which it inherits from the ownable contract, right? And because the proxy constructor is being executed, the owner will be set to the message sender of the proxy. So whoever is currently deploying the proxy will become the owner of the proxy. The proxy then makes new master copy, and the master copy contract also obviously is extending owner, which also means that the owner is set during construction, but it is not set to the same message sender as the proxy, but it is set to its own message sender, and its own message sender at this point, because it is being created here, and create is a little bit like a call, and that means the message sender from the point of view of the master copy is the proxy. So the owner in this case will be the proxy. So storage slot 0 will be set to the proxy address. And then it also has a second storage variable, which is the counter. And it is also setting the counter to 0 in the constructor, but it is not setting the counter to 0 in the proxy. So the counter is not being set to anything in the proxy, but it is still, despite that, equal to 0 because everything is 0 by default. Okay, so when we are calling into the proxy, that means that we are calling its fallback function. So let's say we are calling the proxy with the function signature of increase. So we are hashing this and taking the first 4 bytes and sending it as call data to the proxy. This triggers the fallback function because the proxy itself doesn't have any other function called increase, so the fallback function is triggered. It then looks up in the implementations mapping, it looks up, okay, which address do we have stored for the increase function signature, and it then finds the address of the master copy, and it then makes a delegate call to the master copy. But making a delegate call to the master copy means that now the master copy code is used, but it doesn't make use of its own storage. Its own storage is irrelevant. It makes use of the storage of the proxy, because delegate call is as if you would just take the code of that contract that you're calling and you allow that code to run in your context. You allow that code to run and have access to your own storage. So when we are now calling the increase function on the proxy that makes a delegate call to the master copy does have a increase function, which then is executed, and the first thing it does when it is being executed is it has an only owner check. What does the only owner check do? It checks whatever is at slot 0, and it expects the message sender to be equal to the message sender that was stored in as the owner when the proxy was deployed. And that's why only the deployer of the proxy can call increase. And then if that is true, if the only owner check passes, then the increase function will increment the counter +1 in the proxy, because, as we said, the code is being executed in the storage of the proxy. So the counter in the proxy at storage slot 1 is being increased by 1. So that is once more what is going on here, and I hope that clarified things just in case it wasn't quite there yet. So I hope this helps. Until next time.